Let everybody come back. In the meantime, if somebody wants to ask anything. Okay, so what I was saying was that what I want is this I. I want to write an expression for this I on the right hand side. Now, how do I get the expression for I on the right hand side? If I was just to consider this as a simple electrical circuit, I could have written I as VR over R plus RG, ignoring small r. And I could have just substituted VR as ER R plus RG into small r plus R1. I could have just used this expression. But it is not just this in this circuit. Why? Because now the construction of the galvanometer comes into play, and it is very important to go and think of the construction of your galvanometer. So what all goes into the right hand side I in the circuit? Now, if you go back and list down what we were listing here, what all is happening in my circuit, in addition to these three things that we included on the left hand side, the net EMF in the circuit or the net voltage in the circuit is not just the battery EMF. Why? Because whenever as the coil moves, right, because of this deflection theta t, this coil keeps moving, and as the coil keeps moving, its theta t keeps changing. The flux through the coil keeps changing. How? Now the flux through the coil is given by NB dot A or NBA cosine of the angle between the magnetic field and the area of the coil. Now, as this flux changes, as theta t changes, there is an induced EMF due to this change in flux. This is what you call as Lenz's law. And this comes out to be what? This comes out to be for small angles. I do a derivative here. I get a sine theta, d theta by dt. For small angles, I approximate sine theta as 1. So I get this as NBA times d theta by dt. So now this is an induced EMF, right? And I can write this induced EMF as g theta by dt. And this induced EMF will be such that it's going to oppose.
Won't there be minus sign?
Yeah, sorry? Yeah, there's
Won't there be minus sign?
Yeah, there's a minus sign. There's a minus sign here. There's a minus sign. So there's an induced EMF. There's an induced EMF which is equal to minus g. Sorry, I missed out that minus sign when I took the derivative. Minus g d theta by dt. Right? That's one thing. Second thing. Now, if you look at your coil consists of rings, right? So these rings amount for some amount of inductance in your coil, and as the current changes, builds up in the circuit, there's another induced effect, induced EMF, which is going to oppose this current, right? So the net EMF, hence, in your circuit is then G. So I should not write this as E. Let's call this as not VR. Let's call this as V only. That's why I used an E here. V minus G d theta by dt minus L di by dt. That's the net EMF divided by the resistance in the circuit. Now resistance in the circuit is again R plus Rg plus small r. Let's ignore this small r plus Rg. Now, since the current, so now there is a requirement, that's why here. So if my current is almost is a steady current, this term is going to be extremely small and is going to come into picture if when I turn on and turn off the battery only. So I can very well, for steady currents, ignore that term also. So the net current, instead of just being V by R plus Rg, is actually equal to V minus G d theta by dt, right? So now let's write down our differential equation. So my differential equation is K d square theta by dt square plus A d theta by dt. So on the left hand side, I have all my retarding and restoring and opposing couples plus C theta. Due to inertia, due to viscous damping, due to the phosphor bronze fiber, equal to G times I. That is the couple that's produced when the coil moves inside my magnetic field due to a steady current I, and this is equal to R plus Rg by R plus Rg into V minus G d theta by dt. Or I can rewrite by bringing that G d theta term here, my differential equation as, so you will see there's going to be a G square over R plus Rg d theta by dt plus C theta to G V over R plus G, right? And you've seen this. What is this equation? This equation is nothing but an equation for a driven damped harmonic oscillator, where this is like your gamma, the damping term. You can take this K also here in the denominator and rewrite this equation here. Right? The whole thing. You can rewrite this equation like this, and this equation is nothing but an equation for a driven harmonic oscillator, damped harmonic oscillator, and you know what kind of solutions does this equation bear, the nature of the solution, and hence the nature of the oscillation in your harmonic oscillator is going to depend upon the ratio of this gamma to this omega naught square, which is C by K. That is whether you will have underdamped solution, damped solution, underdamped, critically damped, or overdamped solutions. Is going to depend upon what is the ratio of this term to this term. and this is a driven oscillator. If you keep the key in, eventually the system is going to follow your external driving force, reach a steady state. And what would be that steady state? That is going to oscillate for some time, the transient behavior, and then it's going to reach a steady state. That is, your deflection is going to become some constant deflection, which is going to be given by your driving force. Now, since your driving force is a DC, it's a constant voltage. So what you see that your coil goes, it might oscillate, it may not oscillate, depends upon what is the degree of damping, but go and stop. So this is your 0, stop at some steady deflection. And that's what you do in current sensitivity, is that you keep it. That's why when you do current sensitivity, you want something like this, and you keep the degree of damping to be very large, and you take your galvanometer to be highly damped. We'll talk about that. We'll come to discuss that solution in great detail. And ultimately, the solution is going to be such that your coil is going to achieve a certain deflection depending upon what is the voltage that you are applying to your ballistic galvanometer, right? So what I'm thinking is, I'm going to stop here. Next class, I'm going to discuss the solution to this differential equation and arrive at the final expression for the critical damping resistance. If there's anything anybody wants to ask here, you can ask. Before I break, I will just write it in the form in which I will use it in the next class. Is I'm going to define few constants and write down the final differential equation and then do the solution for that. I'm going to call this quantity here as 2p. The reason why I'm putting the 2 is otherwise I'll have a half in the solution every time. So I'm going to call this quantity 1 by k a plus g squared r plus rg as 2p, and I'm going to call c by k as q squared, and this whole right hand side as some f, which is nothing but gv over k r plus rg. So I'm going to write my equation in a compact form. We know that the general solution to this equation will be what? The general solution to this equation is, you know what it is. We actually obtain theta d to be f by q square, right? Where m is p square minus q square. So you will get here, if p square minus q square is such, if p square is greater than q square, that is if damping dominates over your omega naught, where same condition, gamma being much greater than 2 omega naught, or whatever way you've seen it, right? Then this is a real quantity, and you will get solutions which you've seen, which are decaying solutions. So you'll get real numbers here. But if degree of damping is small, that is p square is much smaller than q square, you get an imaginary solution here, and you will get oscillatory solutions in this part. And here you always have a term like e to the power minus gamma t by 2. It's just that my gamma is your 2, my 2p is your gamma, what you've been used to seeing it. So you get minus gamma t by 2. I've got a p here because I have a 2p here. So I get e to the power minus p by 2. So we're going to deal with this solution next time, looking at different cases and then discussing critical damping. Right? So I'll stop here. If somebody wants to ask anything, you can ask right now. And you can see after a very long time t, if your key is plugged in, after a time t, which is an inherent scale again here, what that time t is when this term becomes 0, right? So then you have a steady state solution. You'll get a steady deflection. This term will die out eventually if your key is plugged in, and if your key is removed, then this term is not there. Then it comes back to 0 after a large time t. Now what is that large time t? That depends upon the comparison between p and t, or just like your gamma and t. We'll discuss that in the next class. So till everybody goes through it, let me take a picture of who all are there in my phone, and then we can, or Aklanja, I can't find my phone. I don't know where have I kept it. Why don't you just click the picture and then you can send me that image of who all are there.
Okay, ma'am.
So nobody wants to ask anything? Aklanja, if you've taken the picture, can we end the meeting?
Yes, ma'am.
Okay, so then we'll meet next Monday as per our schedule. Okay, everyone, see you on Monday then. Bye.
Thank you, ma'am.